this is the continuation of our discussion on Cauchy-Grosset theorem and its generalizations, and of course its consequences. Now let's have a recall. What is Cauchy-Grosset theorem? So Cauchy-Grosset theorem says that if we have an analytic function in a simply connected domain D, then by calculating the contour integral along any simple closed contour is going to be equal to 0. Okay, now let's see it's another generalization of Cauchy-Grosset theorem. Now it is not very apparent why this result is generalization of Cauchy-Grosset theorem, but we will state this theorem precisely, and then we will see how it generalizes the Cauchy-Grosset theorem from simply connected domain to the multiply connected domain. Now what is the precise statement of this theorem? So the theorem says that if we have a domain D, okay, now we can see that there is a hole in this domain D, so it is not simply connected, so it is multiply connected. And if we have two contours, two simple closed contours, and the condition is that this contour C2 is contained inside this contour C1, and of course both these contours are positively oriented or in a clockwise way. And the theorem says that if we calculate the contour integral along this contour C1, then it is going to be exactly the same as the contour integral along this contour C2. Now let's see what is the precise statement of this theorem. So it says that if we have two contours C1 and C2, simple closed contours positively oriented such that C2 lies interior to C1, and if f of z is analytic in domain D that contains both C1 and C2 and the region between them. Okay, so f should be analytic inside this domain D, and this domain D contains C2, C1 and every other point between C1 and C2. Then the theorem says that the contour integral along both contours is going to be the same. Now why it is a generalization of this Cauchy-Grosset theorem? Okay, so remember, what is Cauchy-Grosset theorem? So Cauchy-Grosset theorem says that if we have positively oriented simple closed contour C and it is contained in a simply connected domain, then it is going to be equal to 0. So this is Cauchy-Grosset theorem. Now let's see why this is a generalization of this thing. Now let's consider this contour C, which is basically equal to C1 minus C2. Okay, now we know that there is a condition on C that it should be positively oriented. In other words, if we walk along this contour in the direction of its orientation, then the interior of C should always be on the left side. Okay, so now let's walk along this contour C1 minus C2. Okay, so when we are moving, okay, so let's say when we are moving like this, so when we are moving, we can easily see that the interior of this C1 is always on the left. Now let's once again walk along this minus C2. Okay, so now if we walk along minus C2, which is opposite to C2, which has the orientation opposite to C2, then we move like this. And when we are moving like this, then we can easily see that this interior of C, which is C1 minus C2, is on the left of this path C2. So we can say that this C1 minus C2 is positively oriented. Okay, so if we have this positively oriented contour C, then according to Cauchy-Grosset theorem, this must be equal to 0. Now what is C? Now let's replace C with its value, which is C1 minus C2, and according to the properties of the contour integral, this can be splitted in the following way. So this contour integral minus, or we can just write it down, minus C2, so contour integral along this contour minus C2, so this must be equal to 0. So if this is equal to 0, then this clearly implies that these two contour integrals are equal. Okay, so the contour C1 minus C2 is positively oriented as boundary of this region R between C1 and C2, and hence this contour is 0, and this clearly implies this thing. So that's why this theorem, which is deformation of contour, is another generalization of Cauchy-Gersa theorem. Now let's apply this result and let's evaluate some non-trivial contour integrals. Now let's say Z0 is a fixed complex number and C is a simple closed contour with positive orientation such that Z0 lies interior to C. So the situation is something like that. Okay, so Z0 lies interior to C. Okay, and it is positively oriented, so it is anti-clockwise. Then we need to prove the following thing. Now remember, there is a very special thing about this function, that this function is not analytic at this point Z0. So that's the most important thing here. Okay, so but still we can evaluate its value. Okay, now let's see how to prove this result. Now according to this theorem of deformation of contour, we can replace this contour integral with another contour integral which is along this circle CR with radius R and center Z0. Now remember, this function, this integrand, is analytic at each and every point of the complex plane but the point Z0. So we can just say that our domain D is the whole of this complex plane apart from this point Z0, and this domain D contains this contour C and this contour CR, which is this circle. So according to this theorem of deformation of contour, both of these integrals should be equal to 0. So we can, instead of calculating this contour integral, so we can just calculate the contour integral along this circle CR. So that's our task now, to calculate the contour integral of this function 1 over z minus z0 raised to power n along this circle CR. So how do we calculate contour integral? So we need parameterization of this contour CR. Okay, so this is the parameterization. So once again, it's a circle of radius R and center Z0, and we take the variation of this parameter t to be 0 to 2 pi. Now according to this theorem of deformation of contour, these two integrals are equal because basically this integrand is analytic at each and every point which is between these two contours, and it is also analytic at each and every point of this inside contour CR and at each and every point on the this contour C2, which is outside. So the conditions of this theorem of deformation of contour are satisfied, and hence these two integrals are equal. Now moving on to this very trivial task of evaluating this contour integral. So what do we do? So basically we are just using this condition that f of z dz along C is going to be equal to f of z of t z prime of t dt. Okay, so this is CR in this case. Okay, and the variation of parameter is basically 0 to 2 pi, so that's why we have this 0 and 2 pi, and this is f of z of t. So in other words, just replace z with this z of t. So we just write down z0 plus r e raised to power iota t in place of z minus z0 raised to power n, and this is basically z prime of t. Okay, so this is f of z of t and this is z prime of t, and if we simplify this thing, then we can see that this z0 will be cancelled out with this z0, and what are we left with? So we are left with r raised to power n. Okay, so this is going to be equal to r raised to power n e raised to power iota n t. Okay, so r raised to power n is basically a constant, and similarly from here what do we get? Iota r and e raised to power iota t. So this r raised to power n and this r, they will combine to form r raised to power 1 minus n, and this iota will also be outside this integrand, this integral, and this e raised to power iota n t is basically in the denominator. So what do we get? E raised to power iota 1 minus n t dt. Okay, so that's what we now need to evaluate. Now there are two cases. So the first case is if n is equal to 1. Let's see how do we evaluate in that case, and then the next case is going to be if n is